first up, so let me just give a little logistics first of the day, of the morning. In the back, we've got the mimosas ready for you to make yourselves a mimosa. I figured I better not bartend because I don't know what kind of day you're wanting to have and pour more than you need or less than you want. So, but we've also got the Bloody Marys in the back with all sorts of little things that you can put in them. And but feel free if you want, you can step in the back and you can make yourself a drink during the talks, or if you want to wait between them. We'll have a few minutes just kind of in between each talk to do that. We'll keep the door open. If you need to step out, use the restroom, or if you want to grab more food, feel free. Again, we'll have a few minutes between each talk that you can do that. But the idea of a TED Talk is it's meant to be an engaging talk that you can keep your attention in the sense of short, 20 minutes less than, right in that range of 15 to 20 minute sweet spot. That if you go to a church and your preacher or your priest is going 25 minutes, you just need to stand up. Hey, too long, you've lost it. No, the idea though is they've learned that that's what people's attention spans are really in that range. And so we thought that that's what we could do is shoot for that 15 to 20 minute sweet spot of attention span. So we're going to start with Dr. Ryan Huschka. He is going to speak on the mysteries and miracles of the universe. And he is a full-time professor here. He is an alum. He teaches chemistry or just
physics,
just everything.
TNT, whatever they need me to teach.
Yeah, that's what I was like. I feel like he's teaching all sorts of stuff right now. So I was like, I feel like I'd undersell him if I just said chemistry. So, but he, I emailed him. I was like, hey, do you have an idea? And he emailed me back this topic and then gave the explanation. I was like, I don't even know what that means, but I'm super intrigued to learn about it, and I'm excited to hear about it. So, I'm going to turn it over to Ryan, and we'll get started. Thanks, guys.
Well, thank you. As Daniel said, I am an alum. Graduated in 2007. Went to Houston for grad school at Rice University, and then came back immediately afterwards and started here in about 2012. And I got to be honest with you, this is the first time that I've ever had a mimosa while lecturing. So if this goes well, I might start this trend. And if it doesn't go so well, then maybe not. So we'll see how this goes. So yeah, mysteries and miracles in the universe. I don't know about your experience with science education, but this is kind of my experience. This person right here might be your mom. This might be you as a eager kid, and you were looking up to that parents, and they just have all the answers, right? And it might go on to when you're an undergrad, you did your experiments, and you asked someone, and again, they typically had an answer for your particular question. Your education also might have been something like having a big, large textbook. Science textbooks seem to be these really large books that are just cram-packed with information. Okay? And the idea is to learn all of that information and pretty much overwhelm the student with all of the wonderful things that we know as scientists. However, this is what I kind of like to approach science is we really have no idea. Okay? Which is we have a lot more unknown questions than questions we have answers to. And this is why I like this particular book. It's called We Have No Idea by Jorge Sham. He actually is a director of a comic called PhD Comics. So if you want to pick up this book at some time, it is filled with comics, kind of slapstick humor throughout. Daniel Whiteson is a particle physicist at the University of Irvine in California. And so he was collaborating in terms of the science on this book. Okay? So I'm going to talk a little bit about how this relates to the miracles and mysteries of the universe. All right, so we like to put stuff into data in the science realm, right? So this is what we know, 5%, including pies, dark matter, and, well, the 68%, which we could either label as dark energy or really we have no idea. So let's focus on the 5% of stuff we do know about, and there's even stuff within that 5% that we're still trying to figure out. So the stuff we know, right? So if you learned to a chemistry class or a physics class, you would have focused in on the atom. On the inside of that atom, you would have neutrons shown there in yellow, protons shown there in blue, and then you would have electrons, right, that are circling around that nucleus. And you might ask yourself, right, is that the simplest building block that you could actually get down to? could you go to smaller and smaller than, say, a proton, a neutron, or an electron? So protons and neutrons are actually made up of these smaller particles called quarks. This is where it gets into that particle physicist, Daniel Whiteson. So 6 types of quarks. Up, down, charm, strange, top, and bottom. So if you're asking yourself, are these actual names of particles? Yes, they are. Okay? We didn't just make them up. Okay, we made up the names, and we're just obviously not very good at naming particles. And I think the names are kind of quirky. Okay, I'm not. The mimosa's not helping me be any funnier. So protons are actually made of up, up, down. Okay, so 2 up quarks, 1 down quark. And it turns out that's what gives the charge of a +1 to a proton, because those are the charges there on a up quark and a down quark. So you add up the actual charges and you get to +1. Neutrons, just flip it around, 1 up, 2 down. Okay? And it turns out when you do the charges again, that ends up being 0. So you have a charge of 0 on a neutron. What about electrons? Those are those red spheres circling around the nucleus, and we don't really know exactly where they are or where they're going, which is kind of a problem when you're trying to study them. You can ask Jason Strite back there a little bit more if you want to know a little bit more about the uncertainty principle. I'm sure he can explain better than I. So, as far as we know, electrons are not made up of anything smaller. Okay, so they are a charge of -1, exactly opposite of a proton. They're 1,000 times smaller than protons and neutrons. And it's actually called a lepton instead of a quark. All right, so here's team quarks and here's team leptons. All right? Leptons or quarks are on the left, leptons are on the right. Okay? And again, what's our protons and our neutrons composed of? They're composed of up, down, charge. Okay? So those are the ones, the quarks there are on the left. And what about on the right? We have these 6 leptons. And the only one that we've talked about right now is the one labeled E, electrons. All right? So that means everything that you've experienced, right, in your entire life, all of the matter here on Earth, okay, that we have studied consists of 3 things. Okay? An up quark, a down quark, and an electron. Okay? Which would make us ask the question, right, what are the remaining 9 particles for? We don't know. We know they're there. We've studied them. We've looked at them. We don't know what they're doing. We don't know why they're there. So we call them the useless particles. Okay, they're not quite useless. They're just temporarily unemployed. Okay. But we don't know what they're doing. You want to put it into a little more organized fashion, like we like to do in science, like, say, the periodic table, right? We like to put all of that information into a table where there's trends and things. So there you go, there's all your quarks again, like you guys have mentioned, up, down, charm, strange, top, bottom, those are all purple. You go left to right, they become more massive. Down there on the bottom is the green, so those are the leptons, again, electron. The neutrinos are the kind of interesting ones. There's millions and millions of neutrinos passing through this room right now. Okay, they're probably passing through you, they're passing through the Earth. They're not really interacting with anything, they're traveling very fast. And again, we don't really know exactly what their purpose is. Over there on the red, you have some photons that you've probably heard of. You also have some other particles that are basically force-carrying particles. Okay? So a photon, right? It carries energy from one spot to the next. So radio waves carry energy. UV light carries energy. Visible light carries energy. Okay? So those are force-carrying particles over there to the right in red. And the Higgs boson was actually just discovered, what? Jason, help me out. Do you know when the Higgs boson was discovered? 5 years ago, 7 years ago? Something like that, right? So they predicted that it existed, but hadn't proved that it had existed. So Higgs boson right there in yellow. So that's the 5% stuff we know, right? Consider how much money and time and investment we put into sciences. That's the 5% stuff we know. What about this dark matter stuff? Well, it's first off 5 to 6 times more of it, we think, okay, in the universe than the stuff we know. What is it? This is how I'm going to show you, or the proofs, I guess, to why we think dark matter exists. And what we know about dark matter. It has mass. That's why we call it matter. It has mass, it takes up space. It is invisible. That's why it's dark. It likes to hang out with galaxies. So like say the Milky Way galaxy has a lot of dark matter in it, along with the other stuff like asteroids and stars and dust and debris. So it likes to hang out with galaxies. Regular matter can't really seem to interact with it. Other dark matter can't really seem to react with it either. And it has a cool name. So what are the proofs? All right, so our Milky Way galaxy, in actuality, is spinning around a really massive white part in there, okay? That where you have a lot of mass there with probably a black hole or some area in the middle. So if we were to say our whole solar system is actually one of these little dots, okay? One of these little dots that's spinning around this massive part up here. And what's all the other light parts in there? A lot of other stars in the Milky Way galaxy. So what happens when you put, say, ping pong balls on a merry-go-round and you spin it? They come flying off, right? Okay. This is what actuality should happen to stars as the Milky Way galaxy is spinning if you just account for all the stuff we know. But reality, we know that we are not flying off into space. We know stars are not flying off into space. So something has to be grabbing them and holding them where they are. And we call that dark matter. Okay. So again, there's a more dramatic spinning galaxy. And there's another one. Okay. So the point is, we have to have something that's keeping that particular galaxy together, and we think there has to be something else doing it in addition to all the stuff that we call regular matter. All right, that just sums up what I said. All right, the second proof is something called gravitational lensing. Now, imagine this. You have to use your imagination a little bit on this one. Imagine you are in this part right here in your telescope, okay? And you are looking up into the sky. And as you are up at the sky, okay, you are looking at some far, far distant object. Okay? And that distant object is giving off light. So let's say this is the distant object over here that's giving off light. That's awesome, okay? This particular point source, okay, is giving off light and shoots off light in this direction, okay? But this whole massive thing right here, and this is what we're going to call our dark matter, some huge massive object, okay, is going to bend that light a little bit and come right down here to your telescope. Well, that object can also emit light in the downward direction, and then it bends it comes up to your telescope. What that actually makes it look like in your telescope is that you have the same object in two spots. So you'd look up in your telescope and you'd actually see the same thing, right, in two different spots. It'd look identical, okay, but it would be essentially the same object. And that's one of the proofs. We know that there's something in the middle there that is actually massive enough to affect how light travels. Okay. So if you see that, if you look up in a telescope and you see two things that looks very similar, there's an indication that it might be due to dark matter. I think proof 3 is probably one of the more interesting ones. Every once in a while, okay, we get to see the past. Right? So the stars way out into the galaxies, when they're giving off light, right, they are essentially light that has just reached us. So you're looking at things that have happened millions and billions of years ago. Okay? And so as that light has come to you, one of the things that we got to notice is two clusters actually went and collided with one another. What do you expect when things collide with one another? Destruction, right? Massive explosions, really cool things happening. And that's what happened. So all of the regular matter, the debris and the dust, it exploded. Everything was catastrophe, and it was awesome, okay, because we could watch it and not be affected by it. But also, the dark matter, what it did, dark matter here, colliding galaxies, it just passed by one another. Okay? It really didn't interact with itself. Okay? And so it passed right through itself. That's very odd. That's also really hard to study, right? Our whole science process is based off of being able to manipulate matter, either with charge or weight, okay, or size. Okay? And you can't do that if things are just going to pass by one another. So there you go. Dark matter behaves with gravity, essentially. It's matter, so it affects gravity. But all the other forces that we're used to dealing with in science aren't affected by dark matter. So it makes it really hard to study. All right, so that's dark matter. Dark energy is actually really brief because we really don't know anything about it. but it accounts for 68% of the universe. So we have no idea. Okay? We just know it's there. So maybe I should explain a little bit about maybe what it is. So how do we know dark energy exists? The universe is expanding faster now than it was in the past. Again, you got to kind of use your imagination for this one. So let's go to, say, Thanksgiving dinner. Think about Jell-O that has fruit inside of it. Okay? That good fruit Jell-O dish. Okay? That my kids like and I don't. Okay? That's the one we're going to think about. Your Jell-O is going to be your space. Okay? And your little fruit is going to be stars and planets that are thrown within that space. So when we think about dark energy, don't think about these actual planets physically moving away from one another. Okay? Think about the actual Jell-O expanding. Okay? So what happens when your Jell-O expands? Well, that fruit is going to move away from each other, but the objects aren't actually moving. It's the stuff that contains the objects that are moving. Okay? This is what's happening when we're talking about dark energy. Space is actually expanding. Okay? That's kind of trippy. Right? When you think about it, we're used to thinking of space as just void. It doesn't have anything in it. But in reality, what is space? It's actually a backdrop that contains objects, can be bent, can be warped. If you've ever heard of gravitational waves the last couple of years, okay? Gravitational waves are essentially that space rippling, okay, when some massive collision happens. Some massive collision happens and that space starts to ripple, and we could actually start to detect that with gravitational waves. Okay? So the point is, with dark energy, our universe is expanding, and it really shouldn't, right? Because when you jump off of a 10-story building, what happens? You come crashing down to Earth, right? Gravity is an attractive force. It is not an expansive force. So if something is causing the universe to expand, it has to be energy. So we call it dark because we can't see it, and energy because it's causing the universe to expand. Okay? And the dark side was taken, so we didn't name it that. All right, so how do we know the proportions of 5, 27, and 68? That should be a good question if we don't know what this stuff is. Okay? And for that, I want to point you to the book. We have no idea. Okay? So check it out. It'll give you all the proofs that you're interested in and so much more. So mysteries of the universe. One of the questions I have is, why does science education focus so much on the stuff we know and almost neglect, in a way, right, the stuff that we don't know? I have a lot of students that come in that are really unhappy with uncertainty, right? But if you're going to go into the science field, you should get very comfortable with uncertainty because there is a lot of it. We have more questions than answers, and probably more importantly, we don't know what we don't know. So there's a lot of questions we don't even know if we're asking the right question. We're trying to, but there's a lot of things like dark matter and dark energy. We really don't know how to interact with them, right? We really don't know how to study them. So there's things that we simply probably don't know what to ask or don't know how to answer. All right, the second part of this might be kind of unrelated, but if you're going to talk about the mysteries of the universe, I think from a personal perspective, it's interesting to talk about the mysteries of miracles. A Roman Catholic, and they have fascinated me for a long time. So during Jesus' ministry, he was often asked, will you show us a sign? Okay? So, translation, give us some evidence, right? Healed the sick, cured the afflicted, fed thousands, turned water into wine, raised people from the dead. So what signs exist today, right? What proofs can we look at today? Well, one of them is the Shroud of Turin. Claims to be the burial cloth of Jesus of Nazareth. I'm going to go over these just really quickly. I know I'm running out of time for you, Daniel, so I'm going to go over these kind of quickly in terms of this. It's controversial. This one's controversial. It's actually not even been approved by the Catholic Church. An interesting stat, though, is this particular object has been probably the most well-studied religious artifact. It's 2,000 scientists have studied it, most of which were atheists or agnostics when they started studying it. After their studies, about 95% of them now consider themselves Christian. Okay? Fascinating things. One of the things is, well, how does an image like that get on a burial cloth? Right? Carbon dating, the deep level of detail here. This particular image is actually taken like a photograph, okay, kind of like a negative. So if you look at the regular cloth, it's just kind of like a regular cloth. You really don't see anything. But when you expose it, kind of like you would a camera roll or an old camera roll, this is what you see. Our Lady of Guadalupe, I have a personal, really strong attachment to this because all the times that I went to travel to Mexico. Our Lady of Guadalupe, if you don't know the story, essentially Mary here is an apparition to Juan Diego. Mary asked Juan Diego to ask the bishop to build a church at this particular site in honor of Mary. There's lots of cool things going on here. A lot of the Aztecs believed that the sun and the moon were gods. Notice that she's blocking out the sun and she's standing on the moon. Okay? So this was very powerful imagery for the Aztec people. And essentially the bishop told him, no, I'm not interested in building a church way out in the middle of nowhere. Okay? And so in the middle of winter, there were flowers growing where she appeared. Took the flowers into his tilma. Okay? Tilma was a really cheap piece of cloth, okay, that the Aztec Indians wore. Carried those flowers all the way to the bishop. Bishop wouldn't see Juan Diego, so he waited out there like 3 hours. Finally went into see the bishop, dropped the flowers in front of the bishop, and the image of Our Lady of Guadalupe appeared. So this is another artifact that's been studied by scientists. I'll just read these to you here a little bit. Exposed the elements for over 130 years. Okay? A typical tilma lasts 50 years or less. Okay? So before we preserved it, basically put it in like a vacuum type of sealant. About 50 years or less is what it's supposed to last. It was exposed to the elements, hot temperatures, dry conditions for 130. There's no brush strokes on there. There's no animal or mineral elements in the colors, and synthetic dyes were not invented until hundreds of years later. Right? Which is, how do you get colors on a particular tilma if it's not animal or minerals and synthetic dyes haven't been created? The image is silky smooth, while the rest of the tilma is kind of the scratchy material, as you would kind of expect out of a cheaper type of material. Another interesting thing, when the eyes are magnified 2,500 times, you can actually see people in it at the bottom here that would resemble the people that probably would have seen the image when it was displayed. One of the more miraculous things, I think, is 9 million Aztecs were converted in 7 years as a result of this apparition. Okay? And how did the image get there? Again, the theme of the talk, we have no idea. Okay? Our Lady of Fatima, I'll go ahead and skip over this. This is an interesting website. A young man basically devoted his life. He actually died very young, 21 or 22, I believe. But he dedicated his life to basically writing summaries of the Eucharistic miracles. And there are too many to talk about in this talk. But go check it out, miraculo-eucharistic.org. Very fascinating website. The Incorruptibles. Okay? So the Incorruptibles, again, some of the stories of the Incorruptibles are usually the Catholic Church goes out of its way to hire atheists and to hire scientists that are non-believers in the faith. Some of the stories of the Incorruptibles is they'll do an autopsy, and rather than having that horrific smell of a deceased person, you would usually have, say, a smell of perfume and roses. Okay? When they did an autopsy of the Incorruptibles. And these are saints of the Catholic Church that you can go see in their burial places. So conclusions about miracles of the universe. We have more questions than answers, and to me personally, miracles are just fascinating scientific mysteries that we should try to share, right, as much as possible as believers in the Catholic faith. So hopefully that's good enough. I'm going to drink some more mimosa and answer any questions.